Chapter 12, Optical Fibres, Part 2, Losses in Fibre Optics. A lot of this section of the chapter links back to the Communications chapter, Part 9, and we're not really going to see any new equations, but we're just going to see it in the fibre optics particular area. I should warn you that Chapter 12 is on Paper 2, and Chapter 9 is on Paper 1, which means that these equations can therefore come up in either paper. Okay, so let's talk about different types of losses. There are two main types, attenuation and dispersion. Attenuation is where, as we've already seen, the power of the signal is decreasing, which makes it harder to distinguish between zeros and ones. I remember that all of our signal is digital because we are sending light pulses. So, something strong like this may end up something more like this, and it's very difficult to tell. So that's attenuation. Dispersion is where our signal spreads out. Now, this is a particular problem for fibre optics because we have light and light can get smeared out. So let's look in a bit more detail at both of these. Attenuation has got three causes that we need to be aware of: absorption, scattering, and bending losses. Absorption is where the core or the cladding absorbs some of the light, or some of the photons if you want to go into the physics of it, to be precise. This is due to imperfections, and it does. One of the main area that this is a problem is in the connections between the different cables, which is why usually when they're trying to connect fibre optic cables, they will actually heat them up sufficiently that they can fuse the two ends of fibre optic cable together so that they can try and make the connection as seamless as possible. It also depends on wavelength, because if you know about the photoelectric effect, then you'll know that different energy levels within particles and atoms, different energies can be absorbed more effectively by other things. So you end up with graphs that look something like this, where the attenuation is being measured in decibels per kilometre. And if we compare that to the wavelength, you can see that there are some values that are better for sending down because they have lower amounts of attenuation or absorption. So obviously 1.4 micrometers happens to be a point where this particular material absorbs it really well, whereas 1.5 is obviously a lot better. So that's absorption. Do you make sure you got a quick sketch of the graph? You're not expected to memorize it, but you should understand the general shape. And you may well be asked to analyze a graph if they give you one. Scattering. Scattering is where light is sent in a wrong direction caused, again, by imperfections in the glass. The light that may then interfere with other light travelling down, and it may cancel out if they're out of phase, which is obviously a bad thing because you're losing both the light coming forwards and the light scattering all over the place. Or it may just eventually leave the glass entirely if it's gone beyond, before the critical angle. So that's scattering. Bending losses. So this is, we need the light to hit the core or cladding boundary, be on the critical angle. Otherwise, some of the light is getting refracted, and we remember seeing diagrams previously. So just give me a picture on the slide in a second, where the light would come in and some of it would get refracted that way, going from more dense to less dense, and some of it will get reflected. Obviously, we want it all to get reflected, so we need to make sure that the angle is increased, so it's coming at a steeper angle, so it all comes back inside. So bending can cause a problem because if the cable is bent, then the edge of the material has bent, and so we lose some of the material. So you make sure you sketch this. You may be asked to sketch this to explain it. So that's macroscopic bending, where the whole cable is bent. We can also get what's called a microscopic bend, and that's usually due to a small defect in the glass, and that gets this refraction loss, which is what we've got. So that bit there is getting refracted, and we're not getting total internal reflection, which is what we want. So too tight, microscopic, whole thing, microscopic, tiny, at that point bend. Okay, so we're aware of attenuation. We are going to look at the theory behind dispersion next, but in the interim, let's just do a couple of calculations. As I said before, the equations here are the ones you've already seen in the communications chapter. I would recommend that you pause the video and have a go at both of these parts, this part A, part B, on your own, just so you got a little bit extra practice rather than just watching me. Okay, let's work through this. So we're gaining 15 decibels here and 10 decibels here, so those are both pluses. Whereas this is a negative, this is a loss. And it's 0.4 decibels per kilometer, so the first thing we're going to do is work out what that is. So that's negative 0.4 times 70. So that is negative 28 decibels. So the total gain, where the gain is measured in decibels, obviously not normal units, will be our 15 plus 10 minus 28. So that's minus 3. It's minus 3. And we can now put that into our equation. So we remember that the gain in decibels is equal to 10 log 10 power out over power in. So we've got minus 3 is equal to 10 log 10. The output power we don't know, that's what we're trying to figure out. And the input power is 10 milliwatts. We can divide by 10. Do you make sure you're laying this out really carefully and that you show all your steps of working, because you can get marks for having the right equation and putting the numbers in and steps along the way. And we're going to get rid of the logs. So we are going to do the inverse log or the exponential to get rid of them. So we can now say that 10 to the power of minus 0.3 is equal to the power out over the 10 milliwatts. I'm just going to go up over here, which is about that. So you're just rewriting it and switching them over. Then multiplying by the 10 milliwatts. So the output power is 5.01 milliwatts. So 5.01 milliwatts. Obviously, do watch units. I've left everything in terms of milliwatts, but you could have converted times 10 to the minus 3. So that's the output power. Okay, part B. The signal to noise ratio at the receiver is 28 decibels. What is the maximum acceptable value of the noise power at the receiver? Again, I would recommend you pause the video, have a go at this question on your own. Okay, let's have a look through. So 28 decibels, we just worked out that the output power is 5.01, etc. milliwatts. And I know that the signal to noise ratio, so this is the SNR, is 28 decibels. So I should be reaching for an equation that involves the signal to noise ratio, which is of course in decibels, which is 10 log 10 the power of the signal over the power of the noise. So let's put the numbers in. We've got 28 is equal to 10 log 10 the power of the signal, which is the same as the output power at this point, 5.01 etc. milliwatts. And I'm trying to work out the power of the noise. So very similar to the previous question. You do need to make sure that you're comfortable with this, because obviously this can come up in comms or in optical fibers, or possibly in digital as well, or wireless. So you need to be comfortable with it. I'm just going to go up over here. So 10 to the power of 2.8, taking out log form, is our 5.01 milliwatts over the power of the noise. I'm going to switch the power of the noise over with the 10 to the 2.8. And then put that in the calculator. And this is in milliwatts, 7.94 milliwatts. 7.94 times 10 to the minus 3 milliwatts. Much better to convert into microwatts. So 7.94 microwatts. In other words, much, much smaller than the original signal, or the output signal. Obviously, in these questions, sometimes it will not be, the ambient noise will be given, and you have to work out how big the gain might be in order to make sure that you're getting enough gain that this isn't a problem. Okay, let's talk through dispersion. So dispersion is where the pulse spreads out. And this is obviously a problem because we are trying to send zeros and ones. So if we try and send our pulses too close together, then they'll end up overlapping and you won't be able to tell whether it's a 1 or a 0. So we'll end up with a smear, which we can't read. There are two types of dispersion. There is modal dispersion. This only occurs in multi-mode cable, and that's because the light can travel down multiple paths, which means it arrives at different times, which means it spreads out. So this one in red, C, they're not different wavelengths, just to be super clear, but this one is traveling a lot further. So C will probably be somewhere over here because it's taking a lot longer to arrive. So it'll be, somewhere at the end of the signal. Whereas A, obviously that's going in a pretty straight line, so A is going to be somewhere near the beginning. And you may have B somewhere in the middle, and you end up with this kind of spread going on. A solution for this is to use monomode cables, which only allow one beam of light to pass down. So that is a solution to this. You need to be aware of this solution. Okay, the second type is chromatic dispersion. And this is where you do have different wavelengths of light. All light that we shine down fiber optics, be it laser light or LED light, does have a range of wavelengths, but we can try and the bigger the range, I was about to get the solution, so all light has a range of wavelengths, and the bigger this is, the more chromatic dispersion is an issue. Now, chromatic is to do with color, and obviously different wavelengths have different colors. And wavelengths with one will end up arriving sooner than wavelengths with another. So what's the solution to this? Well, the solution to this is to use laser light instead of LEDs, because it's got a narrower band of wavelengths, so we get less of this. You can't get rid of this completely and utterly. You can't just send down one wavelength, sadly, but you can try and minimize this problem. And that's it. That is 12.2 fiber optics and the losses in them.